Hi everyone! In this lesson, we'll learn about a new type of series, as well as how to quickly calculate its total sum. Let's get started. You should make sure to complete the pre-video activity in your guided notes before watching this video. Pause now if you need time to complete it, then come back when you're done. In the pre-video activity, you discovered that the arithmetic series formula doesn't work for geometric series. Kind of obvious given the arithmetic series formula's name, huh? But why doesn't that formula work? Let's recall what makes that formula so effective for arithmetic series: the constant, never-changing common difference between terms. Terms at the end of an arithmetic series are just as far apart as those at the beginning, so folding the series over on itself creates pairs of terms that add up to the same amount every time, because the differences zero out. This is very much not the case for geometric series, because there isn't a common difference. The change between any two consecutive terms is always different. So it's incredibly unlikely that any pair of terms will have the same sum as another, no matter how you rearrange them. So it seems we're at an impasse. The one formula we know to quickly find the sum of a series only works for arithmetic series. I agree, Mia. There should be a geometric series formula. Let's see if we can logic our way to a geometric series formula ourselves. Within your guided notes, you'll find the Deriving the Formula activity. If you'd like to try it yourself first, pause now and do so, or you can stick around and we'll go through it together. All right, let's see what we can come up with. Here's the generic expansion of a geometric series, which starts at the initial term a, then multiplies by the common ratio over and over. The exponent is always 1 less than the term number, so the nth term has an exponent of n minus 1. The term before that is 1 less than that, and so on. Now to play around with this equation. As long as we keep the two sides equivalent, we can do whatever we want to try to pull a concise formula out of it. Let's try to manipulate this into a nice, succinct formula. The first thing that sticks out to me is that this first term is unlike all the others. It doesn't have an r. I can't just change a single term, so I'm going to multiply the entire series by the common ratio. R times the entire sum increases the number of r's being multiplied on each term by 1, so all the exponents have increased by 1. All right, next. Oh, that's weird. The original sum and the sum multiplied by r seem to have almost all the same terms. In the middle can be assumed to have matches that were just skipped over. The only terms that wouldn't have matches are a in the original sum and a times r to the nth power in the multiplied sum. How could we use that to our advantage? Oh, I know! If we subtract one equation from the other, the matching pairs will be subtracted from each other and zero out. After all that zeroing is done, all that's left is a minus a times r to the nth power. Wow! Just like that, we now only have a few terms to work with. Still, our goal is to find a formula for s sub n, not all this. How could we isolate just s sub n and get rid of the other stuff? Since s sub n is in both of these terms, we'll need a way to pull it out first. We can pull it out through factoring. We can factor s sub n out of both terms on the left, then divide 1 minus r from both sides of the equation to get just s sub n on the left. This is just about done, But both terms up here have an a in them, so let's go ahead and factor that out so there's only a single a in this formula. All right, I think we're done here. All of our steps kept both sides equivalent, so this formula should always give us the same sum of a geometric series as if we added all the terms manually. Let's check whether it works by finding the total sum of this series. Pause the video now and find this sum in two ways, by manually adding together the terms and by using the formula we derived. Let's go over this series together. The first term is 375. The common ratio is 0.2, and there are 5 terms in the series. Since it's a relatively short series, it's feasible to find the sum simply by listing the terms and then adding them manually, for a total of 468.6. Let's see whether our derived formula gives this same sum. We already found a, r, and n, so we substitute those values into our formula. 0.2 to the 5th power is 0.00032. 1 minus that is 0.99968, and we get 0.8 in the denominator. Multiply on top and divide the result by 0.8. Would you look at that? It's 468.6, the same answer we got previously. See, our formula works. We'll call this the finite geometric series formula because it can be used to find the sum of any geometric series with a finite number of terms. Here's a series that we definitely wouldn't want to add up manually. Pause and try using the finite geometric series formula to find the total sum of this series. Then come back so we can go over it. First, let's identify the necessary values. The first term of this series is not -1 over 729 because the series starts with the 8th term in the sequence. We need to find the 8th term in the sequence, which ends up being 3. Luckily, the other 2 pieces of information are easy to find. The common ratio is -3. From term 8 to term 19 excludes the first 7 terms, so there are 12 terms being added. All right, let's make ourselves a little room here so we can use the finite geometric series formula. First, let's substitute. The initial term is 3, the common ratio is -3, and the number of terms is 12. Now we can evaluate. -3 to the 12th power is 531,441, positive, because it was raised to an even power. Now we can simplify the bits of subtraction. Multiply on top, and finally, divide. The total sum of this series is -398,580. That seems like a big total for just 12 terms, but it makes sense. Remember, geometric sequences grow exponentially. And just imagine what would have happened if the common ratio had been positive. Just like with arithmetic series, knowing how many terms there are can be tricky. The same rules still apply to situations like this. Subtract the number of excluded terms from the upper limit to find how many terms are actually included in the series. But what about in situations like this, where the series has skipped to the end instead of having all the terms written out? Can we still deduce the number of terms in the same way we did for arithmetic series? Yes, we can. The overall strategy will be exactly the same. Pause the video now and try to discover the number of terms yourself. First, determine the explicit formula for the sequence that the series is based on. This series starts at 1.5, and each consecutive term is 4 times the previous. Next, substitute the nth term with the last term of the series and solve for n. First, we'll divide by 1.5. This is where things change a little bit, because now we have to solve for an exponent. To get the variable n out of the exponent, I'm going to solve by taking log base 10 of both sides, but feel free to use any strategy you prefer for solving exponential equations. Now the exponent can be pulled down into multiplication, and then we can divide by log 4 on both sides. This looks messy, but we'll clean it up with a calculator. And of course, the final step is to add 1 to both sides. Now we found that from beginning to end, this series includes 9 terms. Now we can use the finite geometric series formula. Pause now and use the information we've discovered to find the sum of this series in your guided notes. Let's check your answer. If you got this as your sum, then you did it correctly. If not, check your work to see where you might have made a mistake. Let's try one final example. Pause and try this example in your guided notes. Then come back to check your answer. How'd you do? Let's find out. First, we need to find out how many terms there are. Start by determining the sequence that generates these terms. Then replace the nth term with the last term in the series. Solve, being very careful when manipulating logs, and you find that n is 11, meaning this series has 11 terms. Now we have everything we need for the finite geometric series formula, so substitute and evaluate. We end up finding out that the total sum of this series is 6,046,617.583, repeating. Great work! Today we learned how to derive the finite geometric series formula, and then used it to find the total sums of finite geometric series. What's wrong, Mia? Good catch! The reason the word finite is in this formula's name is because there's another formula we can use for infinite geometric series. We'll discover that formula and learn how to use it in the next lesson. After you complete your guided notes, make sure to do the lesson activity, and that will prepare you for the online practice. See you next time!
Hey, hey.